So we're going to take a look at the equations that are needed to solve electromagnetic problems. We have our equations up here. A quick reminder of what those letters stand for. F is for force. The units of measure for force is newtons. Q is for charge, and the units of measure for charge are coulombs. Now in our previous units we did learn that the constant for a proton or an electron is 1.6 times negative to the 19. So that's a number we'll be able to use for that Q value on most of our problems. Velocity is the letter V, and the units for that is meters per second. B is going to represent the magnetic field. That's a new one. The unit for this is going to be the Tesla, or capital T is an abbreviation. I stands for current, and the units for that are A, or amps. And L is length, and the units for that are meters. We want to remember that we should be able to convert certain things, so from centimeters to meters, I'll be dividing by 100 because there are 100 centimeters in a meters. In our electricity section, we went from milliamps to amps, and there we divide it by 1,000 because there are 1,000 milli in a millimeter or in an amp. For our problem, we have humans emit a magnetic field. In our blood, we've got ions that are constantly moving, so they're constantly emitting a small magnetic field. This is something that MRIs are able to take advantage of in order to produce those images. And we're going to suppose that an electron whizzes by east across a person standing at a speed of 3.9 times 10 to the 6 meters per second. Well, meters per second is a velocity. So this east refers to that velocity. It says that the electron is affected by a magnetic force of 1.9 times 10 to the negative 22nd newtons. So that will be our force, and that force is directed north. The first question that we have is, how much magnetic field does a person emit? So if I have F and B, that doesn't really help me narrow down my two equations because that's in both. But I do have a velocity. So being as I have a velocity, I know that I'm going to use the Q, V, B equation. Now I didn't actually label anything with a Q, but I did see that word electron. So I know that the charge of any electron or proton is 1.6 times 10 to the negative 19 coulombs. So I'll be able to use that value. I'm going to start out by plugging in the numbers I know. F equals 1.9 times 10 to the negative 22. Q is 1.6 times 10 to the negative 19. B is 3.9 times 10 to the positive 6, and we are solving for the B value. I'm going to start out by combining like terms. Q times V. So when I multiply 1.6 times 10 to the negative 19 times 3.9 times 10 to the 6th, I'm going to get 6.24 times 10 to the negative 13. I'm going to bring down that B value that's missing. I'm also going to bring down that force because I haven't done anything to get rid of it yet. So now I need to isolate this B. Right now I'm multiplying, so the inverse of multiplying would be to divide. So I'm going to divide by 6.24 on this side, times 10 to the negative 13. Whatever I do to one side, I have to do to the other. So 1.9 times 10 to the negative 22nd, divided by 6.24 times 10 to the negative 13. I'm going to use my calculator. And when I do that, I'm going to find out that B equals 3.04 times 10 to the negative 10. Being as this is the units for magnetic field, I'm going to use T for Tesla. To determine the direction of my magnetic field, I need to use my right-hand rule. So for my right-hand rule, I'm going to look at I'm going to be solving for the field, which is my fingers. And they told me the direction east, which referred to the velocity. So that's going to be my thumb. And they also told me this direction south, which was referring to the force, which is indicated by my palm. Now since they told me it was an electron, I'm going to know that as an electron, it's the inverse of our current. So I'm going to use my left hand rather than my right. So using my left hand, I need to find a way to make my palm point towards the north or away from the camera, while my thumb points towards the east or to the right. So I currently have my thumb pointing to the east or to the right, but I'm going to have to adjust to make my palm point where I need it to be. So right now my palm is pointing down to the paper. If I go this way, my palm will be pointing south. So if I keep twisting this way, now my palm is pointing north, My thumb is still pointing to the east, but my fingers are pointing straight up into the air. So my fingers are the magnetic field. So that means that the magnetic field would be pointing straight up into the air or up and out of the paper. So the direction of my field would be up or out of the page, or you could use the indicator of that dot to represent that it's coming out. So any of those would be good ways to describe that magnetic field. For our second question, we're going to see an example of a wire that is 1.5 meters long. So that will be represented by my L in the equation. It is carrying a current of 10 amps. So that's going to be my I. So that current is directed to the top of the page. So that'll come in handy in a little while when I'm doing my right-hand rule. The charge is affected by a uniform magnetic field, and the force is acting at 0.6 newtons, so that's my force, and it's directed to the right. So again, that'll come in handy in a second. To find my magnetic field strength, I'm going to be solving for the letter B. So I have L, I, F, and I want B. The equation that I'll be using is F equals BIL. Instead of force, I'm going to use 0.6 newtons. I don't have a B value, so I need to leave that alone. My current, or my I, has a value of 10, and my L has a value of 1.5. Just like in the previous problem, I want to start by combining like terms. So 10 times 1.5, that's 15. I'm going to bring down that B, and I'm going to bring down my 0.6 newtons of force. Now I need to isolate B, so the opposite of multiplying by 15 is going to be to divide by 15. If I do it to one side, I need to do it to the other. So in my calculator, I'm going to do 0.6 divided by 15. 0.6 divided by 15 is going to give me a value of 0.04. Because that's the field strength, the unit will be Teslas, or the capital T. So now to do my right-hand rule to determine the direction of my field. So I'm using my right hand because it's referring to current. I'm going to take my thumb, and it's going to point towards the top of the page. So my thumb needs to point to the top. And we're going to be looking for where our fingers have to go. So to point my thumb to the top, I can have my palm face up, I can have my palm face down, I can have my palm facing to the left, and a little bit more uncomfortable, I can have my palm facing to the right. So to determine which direction to face my palm, I need my palm to be going my force to the right. So with my thumb facing to the front and my palm facing to the right, my fingers, in order to accommodate that, will need to be moving upward towards out of the page towards the ceiling. So the direction of my field would be up and out of the page as my fingers show. So the last type of problem that we're going to solve is going to be a transformer problem. And in transformers, we're comparing the number of wires that we have on one side to the number of wires that we have on the other side. So we refer to the incoming amount as a primary. So the primary is what happens first, what goes into that transformer. And the secondary is going to refer to what happens second, or what goes out of that transformer. So we need to be able to group the voltages as well as grouping the like times. So the primaries together and the secondaries together. And that comes from reading in some context clues. In our example, we have a power line that carries 50,000 volts before. Before is a key word that it happened first, so it must be my primary. It is stepped down to, so it happened after 110 volts as it enters the house. So every time I see something refer to a house, I know it's going to be referring to my secondary term. So if the houses, or the secondary coil, has 100 turns, then how many turns does the power company side, which would act as my primary? So that'll be my question. So to form my proportion, I need to isolate the primary voltage and the secondary voltage and set that equal to the primary number of turns and the second number of turns, or number of coils in the wire. So my primary voltage was 50,000. My secondary voltage was 110. The primary numbers of turns is what I'm solving for, and the secondary number was 100. So I'm going to start out by cross multiplying. 50,000 times 100 is 5 million. 110 times x is 110x. Now I'm going to solve for x isolated. So I need to divide by 110 in order to do that. So this goes away, and 5 million divided by 110 is going to give me a value of 45,454.54 turns. So that'll be my final answer. Relating it to some of the previous units that we've already done, the previous information we saw in our rotations, when we had a higher voltage side, that side seemed to have more wire and it was thinner. And so this follows that same pattern. If the smaller voltage has 100 turns and our larger voltage has 45,000 turns, then we follow that pattern of a higher voltage having more wire, and it would likely be thinner.